In this section of the text, we're going to look at naming and writing formulas for molecular compounds, which also refers to covalent compounds. Now, if you think back to the ionics, there were so many rules. We had to know how to find all the charges. We had to then make the compound neutral or crisscross the charges. We had to deal with the transition metals that had multiple charges and put Roman numerals in and figure out the Roman numeral. And then, oh gosh, it never ends. There were polyatomic ions that are groups of atoms that all had a charge, and we needed parentheses, and it was just a lot, right? But it took us a couple weeks to really master the art of writing an ionic formula. And the covalents might take us maybe 20 minutes. So here are some rules for naming covalent or molecular compounds. Number one, we have to identify that the compound is covalent and thus can follow these new set of naming rules. And so when we think about the covalent or molecular compounds, I should remember, they're a little smaller, that they are all non-metals. So if you have a compound and you notice right away it's like carbon and oxygen or phosphorus and chlorine or whatever it might be, if it's all non-metals, it's covalent and you can proceed with these new naming guidelines. If it's metal bonded to non-metal, it's ionic. And then we're going to be a freak about charge. We're going to look at our periodic tables to find the charges. But with covalents, you don't have charges. Charges come from transferring electrons, gaining and losing electrons. But we're not doing that with a covalent or molecular compound. We're just sharing the electrons. And while sharing the electrons doesn't create a charge, it means then that we need some new way of indicating how many atoms of each element are in the compound. When I had the charges, I knew how to write the formulas because we got the little subscripts by trying to either crisscross the charges or make them neutral by balancing the charges. And I'm not going to have that now. So instead, it's even easier. You're going to use these prefixes. We're going to use these prefixes to indicate how many atoms of each element are in the formula. And now, for example, here they're showing me carbon and oxygen. Carbon and oxygen can bond together in different ratios. It depends on if they're single bonds, double bonds, triple bonds. I mean, that can create different formulas. Now, we can also have the same situation with an ionic compound where, I could have different forms of manganese and oxygen. And it would depend on the charge. I mean, oxygen is always -2. Well, if manganese was +2, then it's neutral. And my formula would be MnO. And manganese could also be, let's say, +4 is a common charge. Oxygen -2. Well, now I either crisscross or balance it out, and I'm going to need 2 oxygen to make it neutral. So it happens with ionics too, where we could have the same elements bonding together in different ratios. Well, then that's because the charge on the manganese was different. Here with something like carbon and oxygen, we could get different ratios because they're sharing in different ways. We could share a double bond, a single bond, a triple bond. And so I need to be able then to indicate the number of atoms in the formula by using these prefixes because I don't have charges. So if you have something like carbon and oxygen in a 1-to-1 ratio, the prefix that means 1 is mono. Now you could say monocarbon, monooxide. That wouldn't be wrong, but often when there's only one atom of the first element, we probably are going to see that mono omitted only if it's on the first element. Now, if somebody wrote on a test monocarbon, monooxide, that's fine. Or again, sometimes then we might stop it. If there's like a double vowel, instead of saying monooxide, we might just write monoxide. But I promise I won't mark it wrong if you say monocarbon monoxide. It's just that we often don't need mono if it's the first element that's only one. But I have to indicate the second element with monoxide. Now CO2 then, I don't have to say monocarbon. I could, but often we don't put on the first element. But then you will always see a prefix on the second element. So the prefix that indicates 2 is di. So carbon dioxide, which you've heard of your whole life, right? We always talk about carbon dioxide or even carbon monoxide. It's deadly. But it's that prefix then that can get you back to the formula. And so it's really simple. We don't have to worry about charges and making them neutral and crisscrossing or polyatomics and Roman numerals. We just need to be familiar with this chart of prefixes. And most of them are probably things that you're familiar with. Mono 1, di 2, tri 3, tetra is 4, penta is 5, hexa for 6, hepta 7, octa is 8, nona is 9, and deca for 10. So in question 30, there are different forms of chlorine and oxygen that bond together. And so we want to write maybe the names. How do the names of these compounds differentiate one chlorine oxide from another? Well, the names are going to have those prefixes indicating how many atoms of each element are bonded together. So if I have ClO2, I don't need to say monochlorine. You could just say chlorine. But you'll always put a prefix on the second element. So 2-oxygen would be dioxide. And if I see the word chlorine dioxide, I can simply go back to the formula. Chlorine, well, there must be 1 if there's no other prefix. Di means 2. Dioxide, 2 oxygen. No charges necessary. We're not transferring electrons. Now the other one, Cl2O3, I would put dichlorine on the first element. As long as there's not 1, then you will see a prefix on the first element. And then 3-chlorine would turn into trioxide. And so the first element will also have its normal name written out. We just add a prefix. And the second element will end in IDE. So I guess that's somewhat similar to the ionics. But the big difference is no charges. We use these prefixes. So much easier, right? So here's another example. If I saw a name, dinitrogen tetroxide. And so here might be a situation where we dropped a double vowel. Tetraoxide would be fine. If you wrote tetraoxide, I will not mark it wrong. But you might also see just tetroxide. And so di means 2, tetra is 4, done. N2O4. And now what you'll notice is this is okay. Notice that it's not the simplest ratio. 2 to 4, that's not the simplest ratio. But that's okay if covalent. If covalent. Covalent compounds exist as molecules. That's why sometimes we call them molecular compounds. This would just be 2 nitrogen atoms and 1, 2, 3, 4 oxygen. And that's just the true structure of the molecule. It just is a bigger molecule that has 2 nitrogen and 4 oxygen. And like here could be another one. Nitrogen, nitrogen, oxygen, 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 oxygen. And so it just exists as these molecules, and there really are 2 nitrogen and 4 oxygen. This would not be okay if it were ionic. Ionics are just a little different. With an ionic, we try to write the formula as the simplest repeating pattern of the crystal. And so you remember ionics were these crystals that had the charged ions packed real tight together, positive, negative, all the way through the crystal, where it's not individual molecules. You can't tell where one molecule starts and another molecule ends. It's just a bunch of oppositely charged ions that form this very organized crystal pattern. But then we try to write the formula as the simplest repeating pattern of the crystal. So if I had something like my manganese, like Mn plus 4, O minus 2. Well, if I'm a charge balancer, I see that, oh, I got a plus 4, a minus 2. I just need 2 oxygens to make it neutral. But if you were a crisscrosser, here's where you'd have to be careful. Because if you had a plus 4 and a minus 2, and you try to crisscross those charges, now you're going to end up with something that is not the simplest ratio. You'd have Mn2O4, and that's not okay. Sad face. Not okay if ionic. If it's ionic, which means there's a metal and a non-metal and charges. Now it's not okay. Not okay if ionic. Then I need to simplify it. All right, so then question 31. There are many compounds composed of nitrogen and oxygen. Compare the formulas of nitrogen monoxide and nitrogen dioxide. So easy, right? You just use the prefixes. There's no prefix on the nitrogen, so it must be 1. Monoxide just means 1 oxygen. Nitrogen dioxide means 2. Done. Now don't overthink it. That's done. Now these guys bond in different ways. They can bond with single bonds, double bonds, triple bonds, and that gives us different formulas. But now don't turn into a bonehead and try to put charges on these guys. When your compound is 2 non-metals, there are no charges. We're not going to transfer electrons, and that then does not create a charge. So I have people that will turn into boneheads because they just overthink it. It's that easy. Let it be easy, right? Take it for once. It's easy. And they'll say like, okay, I have nitrogen and oxygen. And they'll be like, nitrogen is a -3 and oxygen is a -2. And then they'll get really stumped because they'll say, well, I don't know what to do. I mean, they're both negatives and I can't bond 2 negatives together. Well, you're right. You can't bond them ionically. You cannot bond nitrogen and oxygen and give them a full outer shell by transferring electrons because they both need to gain a few. There's nobody that's willing to donate a few. So yeah, that can't happen ionically, but it can happen covalently. So don't put charges up there when it's 2 nonmetals. They can share, and if I wanted, I could draw the Lewis structures and figure out what they look like, but they're going to share electrons, and so there are no charges. When you see these prefixes, that's another indicator that, oh, cool, it's covalent, it's all nonmetals. I'm going to take this for a nice, easy question. Awesome. So then here are just a couple other quick examples. The disulfur dichloride kind of follows along with that last example. It's really 2 sulfur and 2 chlorine. Done. That's it. You don't have to simplify. And I could draw the Lewis dot structure, and I could really bond 2 sulfur and 2 chlorine. And that would be okay. That's the true structure of the molecule. No simplifying necessary, and no charges. With the N2O, you've got 2 atoms of nitrogen, so that's dinitrogen, 1 oxygen, monoxide or monooxide. Now, the mono has to go on the second element. There will always be a prefix on the second element. It's just that if mono were on the first element, we might drop it. But again, those prefixes are really important because you can't tell me, hey, go in the lab and get some nitrogen oxide. Because I would say, well, which tank? I've got a couple different nitrogen oxygen gases in the lab. So you'd have to tell me which one. Oh, we'd indicate it with the prefixes. Kind of like with transition metals, you would indicate the charge with a Roman numeral. So let them be easy. Something like 32, name this compound. Tetra is for, this should have been tetraphosphorus. So the first element gets his normal name, and then the second element will still change to IDE. So 3 sulfur would turn into trisulfide. Done. Writing the formula for carbon tetrachloride. There's no prefix on the carbon, so it's assumed to be 1. Tetra is 4. Cl for chlorine. There are 4. It's really that simple. No charges necessary. And you don't have to simplify. That is the true structure of the particle. You could draw the Lewis dot structure if you really want to. Put the 2 sulfur in the middle, and then the 2 chlorine would go on the outside. That's the true structure of the molecule. But that would only be true if it's covalent. You could not have something like Mg2O2. That would be a sad face. With there being a metal, it's ionic. And then I would need to simplify. Awesome. So then finally, speaking of ionics, question 34 goes back to this whole idea of like gems and ionic gemstones and crystals. Many gemstones are silicates. There is one called peridot. It is a yellowish green gemstone containing the orthosilicate ion. Not one of the most common polyatomic ions, but it exists. SiO4 minus 4 or 4 minus. In the form of peridot called forsterite, the orthosilicate ion bonds with magnesium. In another form called phthalate, iron 2 bonds with the orthosilicate ion. Write the names and formulas. Well, the name is just that. It would be magnesium orthosilicate and iron 2 orthosilicate. Now when I go back to these ionics that have charges, now I'm obsessed with making it neutral or crisscrossing. So magnesium is in the group on my periodic table that is always a +2. And then this orthosilicate ion is SiO4. And then the charge is 4 minus or minus 4, same thing. Okay, so you could either crisscross or be a charge balancer. If I'm a charge balancer, I'm going to get the right answer immediately because I'm going to say, oh, +2 minus 4, I need 2 magnesium. Then that multiplier, boop, 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 would become my subscript. Mg2, SiO4. I'm done. Now I don't have to put parentheses around the silicate ion because I only need 1. If I needed more than 1, then I would put it in parentheses. Now you could also be a crisscrosser, and we're talking ionics here. Because there's a metal bonded to nonmetals. It could be one nonmetal or it could be a group of nonmetals, a polyatomic. So now I've got iron Roman numeral 2, which just means the charge is +2. And then the orthosilicate ion was 4 minus or minus 4. And so now here, if you're a crisscrosser, you would just have to be careful, because if you crisscross a 4 and a 2, I would need to simplify those. Or if I left it like that, I would need like a parentheses around the SiO4. So now I would need to simplify that, and my formula then should be pretty similar. SiO4. Both metals, magnesium and iron, were +2, so they should give you very similar formulas. But I only worry about simplifying and charges if it's ionic, meaning there's a metal. The covalents are really that easy. Just let the prefixes tell you how many atoms of each element are in the compound.